We have a ball bouncing vertically on a hard surface after being thrown up into the air by a boy standing on the ledge of a building. So what's going to happen is the following. Let's draw a little bit of a picture. Here's the ledge of the building. The ball goes up. It slows down, and that's that part of the journey. The next part of the journey is where the ball gets back to its original starting point, whatever that is. Then it continues down to the ground. On the ground is where it is going to bounce, and it bounces up, and that is all that they depict in this picture over here, up to that point over there. Just to watch carefully what happens, they tell us, just before the ball hits the ground for the first time, it has a velocity of 15 meters per second. They tell us that. Immediately after bouncing, it has a velocity of magnitude 10 meters per second. It's obviously in the opposite direction if it's bounced. And notice that energy was not conserved because it had 15 meters per second in it, and it left with 10 meters per second, and therefore it lost some energy during the actual bounce. What's also important to recognize is that point A over here and point B on the graph are really in exactly the same position in the bounce. They are on the ground. The graph below shows the velocity as a function of time from the moment it is thrown upwards into the air until it reaches the maximum height after only one bounce. Down, bounce, maximum height. Use the graph to prove that there was no significant air resistance acting on that ball. And so what I'm going to do is I'm going to take air resistance would mean that gravitational acceleration would be less than 10. So I'm going to work out the gravitational acceleration. Remember, from a velocity time graph, I can get acceleration using the gradient. So I'm going to get the gradient, and I'm going to say A is equal to change in y minus 15 minus 5 over change in x 2 minus 0, and I land up with minus 10 meters per second squared, which is 10 meters per second squared downwards, and we can then say that that is gravitational acceleration. Gravitational acceleration is at its full value, therefore there is no air resistance. How far below the point of release does the ball hit the ground? So now we are interested in this height over here with the green. So we do know that if it went up into the air at 5, it would have come down to there at 5 as well. I can also use my equations of motion very carefully and set up a equation of motion. So let's go. My initial velocity at the very start of this motion is 5 meters per second up. By the time it's at the bottom of the ledge, it is 15, so I'm talking about this point over here, it is going at 15 meters per second down. Acceleration is 9,8 meters per second squared down. Notice how I'm going through writing this list down, and I know what I'm doing, but it's really important that you can clearly see all the information that you've got. What are you interested in? You're interested in the distance, so you can go v squared equals u squared plus 2as. In other words, not using time, although you do have time as well. You have those 2 seconds. But then it becomes a little bit tricky, because if you use the 2 seconds and the 9,8, truth be told, as I said in the last video, this gradient is actually 10. So your numbers go a little fuzzy, and you need to just watch your method more carefully than anything else. So final velocity, I'm going to say, is 15, but it's down, so I'm going to make it negative, is equal to 5 squared plus 2 minus 9,8 s. And s turns out to be 10,2 meters. If you had used the 2 seconds, I think you land up with 9,6 meters, and if you use 10 meters per second squared, as your gravitational acceleration, you'll end up with 10 meters. So anything around 9.6, 10.2, 10-ish, depending on exactly which values you used, because of the discrepancy between this gradient and the fact that we now use 9,8 meters per second squared as an acceleration. The next question, use an equation of motion to determine how long it takes from the time the ball was thrown for the ball to reach its maximum height after bouncing. So it's all the way down there and up again. We know this first part of the motion took 2 seconds. So we can just calculate the time for the second part of the motion. And for that second part of the motion, you are going to need to, your initial velocity is 10 meters per second up. Your final velocity, just until the top of the bounce, is 0 meters per second. Your acceleration is 9 meters per second, 9,8, meters per second squared down. I'm interested in the time. V is equal to U plus AT. 0 is equal to 10 up plus minus 9,8 because it's down, T, and my T comes out to be 1,02 seconds. If you use 10, obviously it would have come out to be 1. I then say total time is equal to 2 plus 1,02, which is equal to 3,02 seconds. The last question, what is the position of the ball measured from the point of release when it reaches its maximum height after bouncing? So I want to know the difference between these two heights. That's what's interesting to me. So what I'm going to say is well, what was its maximum height above the ground? Let's find that out. And once I know that, I can start relating it to my other position and my other height. So I'm going to say I've got these 10 meters per second upwards. My final velocity is 0. My acceleration is a. What is the distance? So let's go. V is equal to, V squared equals U squared plus 2AS. It's not very visible. So 0 is equal to 10 squared plus 2 negative 9,8 and S. So my distance is equal to 5,1 meters. So this height over here is 5,1. I had already worked out this height to be 10,2. So 10,2 meters minus 5,1 meters conveniently turns out to be 5,1 meters up. Obviously, if you didn't have 10,2 here, you had 9,6, you'll have a slightly different value. If you use 10 over here instead of 9,8, you'll have a slightly different value. So just double check your method.